Hello and welcome to the session on Semaphores. Before we move forward, here is the learning outcome. At the end of this session, students will be able to uniquely identify the semaphore in process synchronization. What is mutex locks? Mutex locks are generally considered the simplest of synchronization. Here in this session, we discuss on a tool that can behave similarly to a mutex locks but can also provide more classy way for processes to synchronize their activities. A semaphore S is an integer variable that apart from initialization is accessed only through two standard atomic operations, that is wait and signal. The definition of wait is as follows. All modifications to the integer value of a semaphore in the wait and signal operations must be executed indivisibly, which means that when one process modifies the semaphore value, no other process can simultaneously modify that same semaphore value. The definition of wait shown here on the slide. In addition, in the case of wait, the testing of integer value of s is less than or equal to 0, as well as its possible modifications, that is s minus minus, must be executed without interruption. The operating system often distinguish between counting and binary semaphores. The value of counting semaphore can range over a restricted domains. The value of a binary semaphore can range only between 0 and 1. Therefore, binary semaphores behave similarly to the mutex locks. However, in fact, on systems that do not provide mutex locks, binary semaphores can be used instead of providing mutual exclusions. Counting semaphores can be used to control access to a given resource consisting of a finite number of instances. The semaphore is initialized to the number of resources available or the resources available. The semaphore is initialized to the number of resources available. Each process that wish to use a resource which performs a wait operation on the semaphore, which means that decrementing the count. When a process releases a resource, it performs a signal operation, which means that incrementing the count. When the count for a semaphore goes to 0, all resources are being used. After that, the processes that wish to use a resource will block until the count becomes greater than 0. Here, we can use semaphores to solve various synchronization problems. For example, as shown here, consider two concurrently running processes, P1 with a statement S1 and P2 with a statement S2. Suppose we require that S2 be executed only after S1 has completed. Here we can implement this by allowing P1 and P2 share a common semaphore sync initialized to 0. So in process P1, we insert the statements. The definition of wait and signal semaphore operations just discussed in the previous slide. To overcome the need for busy waiting, so we can modify the definition of the wait and signal operation as follows. When a process executes the wait operation and finds that the semaphore value is not positive, it must wait. However, rather than engaging in busy waiting, the process can block itself. The block operation places a process into a waiting queue associated with the semaphore, and the state of process is switched to the waiting state. After that, the control is transferred to CPU scheduler, which selects another process to execute. A process that is blocked waiting on a semaphore S should be restarted and when some other process executes a signal operation. The process is restarted in a wake up operation, which changes the process from the waiting state to the ready state. The process is then placed in a ready queue. The CPU may or may not be switched from the running process to the newly ready process, depending on the CPU scheduling algorithm. To implement semaphores under these particular conditions, we define a semaphore as follows. So here the definition of semaphore. Each semaphore has an integer value and a list of process list. When a process must wait on a semaphore, it is added to the list of processes. A signal operation removes one process from the list of waiting processes and awakens that processes. Here you can see the wait semaphore operation can be defined as the signal semaphore can be defined as the block operation suspends the process that invokes it. The wake up operation resumes the execution of a blocked process P. These two operations are provided by the operating system as a basic system calls. Here you have to note that semaphores values may be negative, whereas semaphore values are never negative under the classical definition of semaphores with busy waiting. If a semaphore value is negative, its magnitude is the number of processes waiting on that semaphore. This fact results from switching the order of the decrement and the test in the implementation of wait operation. Here, the list of waiting processes can be easily implemented by a link field in which the process control block, that is PCB. Here, each semaphore contains an integer value and a pointer to a list of PCBs. The one way to add and remove the processes from the list so it has to ensure the bounded waiting is to use FIFO queue, where the semaphore contains both head and tail pointers to the queue. The correct usage of semaphores does not depend on a particular queuing strategy for semaphore lists. It is the critical semaphore operations to be executed automatically. Here, we have to guarantee that no two processes can execute wait and signal operation on the same semaphore at the same time. Because this is a critical section problem, and in a single processor environment, we can solve it by simply inhibiting interrupts during the time of wait and signal operations which are executing. So this particular scheme works in a single processor environment because once interrupt is inhibited, instructions from the different processes cannot be interleaved. Only the current running process executes until interrupts are re-enabled and scheduler can re-again control. In a multiprocessor environment, interrupts must be disabled on every processor. Otherwise, instructions from different processes may be interleaved in some arbitrary way. Disabling interrupts on every processor can be a difficult task and it can be seriously diminish performance. Therefore, Systems must be provide alternative locking techniques. Here, pause the video, think and answer. The answer is C. Here is my reference. Thank you.